So hello everyone, I'm Norman Wildberger. We're here at the University of New South Wales. Today we're going to talk about the Frenet-Serret equations, which tell us about curves in space and extend our notion of curvature to another related concept called torsion. So I'm going to start with the planar case to motivate things. So we were talking about this unit circle at the end of the last lecture. No, it wasn't a unit circle, it was a circle of radius a and a curve going around it, parametrized by essentially the angle, which we're going to call t, because we like to think of the parameter as being time. And here was the formula for the curve itself, alpha of t, a cos t and a sine t, and here was its derivative, alpha prime. And we noted that the size of the derivative was equal to a. So this is a constant speed curve, but not unit speed, unless a equals 1. Now it's often nice for us to try to reparameterize the curve. So we want to reparameterize by introducing or use arc length s as a parameter. And our arc length is defined by the formula that it's the integral from over the curve, or whatever part of the curve that we're considering, of the alpha prime of t dt. So in this case, in the circle case, the arc length at a certain point, which we can denote by s there, that represents the arc length, just the length of the curve from wherever we started, let's say we're starting here, to the point where we're at. So in this case, s is just equal to, well, the integral over the of a dt, so that's a times t. So we can reparameterize in this case very simply just by replacing t with s over a. All right, so what would happen there? So we would get a slightly different curve, not much different, but it's just slightly renormalized. And I'll generally tend to use beta to signify that we're talking about a unit speed curve. So beta of s, at least in the plane, is going to be a cosine s over a and a sine s over a, just replacing the t with s over a. And then we can calculate its derivative, b prime of s will be minus sine s over a, comma, cosine of s over a, because the a's cancel. And then we can check that in this case, yes, the length of the derivative, b prime of s, is indeed 1 for all s. So this is indeed a unit speed curve. Its velocity has length 1 at all times. And the acceleration, beta double prime of s, one more derivative, we're going to get minus 1 over a, cosine s over a, and minus 1 over a, sine s over a. And that's a vector pointing in the opposite direction from where we started. So maybe our tangent vector, beta prime of s, and then beta double prime of s will be in this direction. And its speed is, or its length is, the length of beta double prime of s is, well, still just this squared plus this squared, the cosquareds and sine squareds will still add up to 1. And we'll just get square root of 1 over a squared, which is 1 over a. which is, in this case, the curvature of this circle. What we usually call in K. So we see that for a circular motion, if it's unit speed circular motion, then the length of the tangent vector is 1 because it's unit speed, but the length of the acceleration, the second derivative, will be the curvature. I should write curvature K here. So this motivates us to think of the size of the acceleration vector as being how we can define curvature in a more general setting. So we use this to define curvature for more general curves. In particular, curves in space, which is what we're going to be talking about today. But before I do that, let me just write down one more formula for the normalized acceleration vector. What we get when we normalize by dividing by the length. So if we normalize and write, say, n of s, which is going to be beta double prime of s over the length of beta double prime of s, then that's going to be, well, we're just dividing by the 1 over a, so that's going to be just minus cosine s over a minus sine s over a. That's going to be a unit normal. So on our picture, well, we don't know what A is, where the 1 is in this picture, but let's say, suppose that the 1 happened to be, let's say there's 1, for example. Then that would maybe roughly be, that's supposed to be our tangent vector with length 1. So in that case, then the normal vector, which we've renormalized beta double prime of s, renormalize it so that it has length 1, well, it'll be something like this. So there will be n of s, pointing in the same direction as beta double prime, but just of length 1. So now we have these two vectors. They are perpendicular in this case, and they're both of length 1. This is the normal vector. This is the tangent vector here, and we're going to call it t of s, and this is the normal vector n of s. All right, so we now want to take this motivating example and start thinking about curves in space. In particular, we're interested in, say, a curve something like this. Okay. There's a curve in space. We're interested in analyzing it. Okay. So as we move along the curve, we have to choose a direction. So let's say we choose this direction here. So at any point, we can talk about the tangent vector will be in the direction of the curve, clearly. And of course, the speed of the curve, the velocity, will depend on how fast we're going. But we want to perhaps think about a unit speed curve to make things sort of simple. If we think about a unit speed curve and say this is a unit vector, then our tangent vector is going to always be the same size, and it's just going to be exactly like this kind of vector, moving steadily along at the same pace all the way around. But it's moving. And what we're interested in doing when we're studying the Frenet-Serret equations is thinking about not just the tangent vector, but also a normal vector, a unit normal vector, which is playing just the same role as this one is, which is in the direction of the acceleration. And then in addition, with a right-handed frame, a third vector called the binormal vector, which is going to, together with the tangent and the normal vector, the binormal vector is going to form a right-handed system of 3 unit vectors, like I, J, and K. Okay? And what's going to happen is that as we traverse whatever curve we have, okay, maybe I'll go over here. So let's suppose that we're here. Okay, so I'd have to orient myself so that the blue is going in the direction of the tangent, and the red one would be in the direction of the normal, and then the binormal would just be perpendicular to it. And we're going to watch these 3 vectors move along as we go along the curve. Right? So what we're going to have is these 3 vectors are going to be moving in space, and they're going to be twisting as well as as going along the curve. Right? And the Frenet-Serret equations tell us how these 3 vectors are changing. Give us very precise formulas involving the curvature and this other quantity called the torsion that allow us to completely control what's happening in this unit speed case. All right, so that's what we're going to do. And before I get into the real business, I just need a little bit of preliminaries. So just some differentiations of vector quantities. Okay, so we're going to be thinking about having vectors which depend on time. So I'll write R of t, but most of the time I will be thinking of a vector R of t. And typically it has components, x of t, say y of t, z of t. And if we have some other vector valued function, s of t, which is also officially a vector, maybe it'll have components x prime of t, x prime is not good, maybe x hat of t, y hat of t, z hat of t. Then we can perform 2 standard things with these 2 vector valued functions. We can first of all define the dot product between them. So r of t dot s of t is just the obvious thing, x of t, x hat of t, plus y of t, y hat of t, plus z of t, z hat of t. And that's actually a number, which is actually a function of t, because the dot product of the 2 vectors is a number. So that's actually a single valued function of t. Maybe we'll call it f of t. And another thing that we can do, of course, is we can take the cross product between these 2 vectors. So r of t cross s of t equals, okay, well, it's a vector, which is going to be y of t, z hat of t, minus y hat of t, z of t. That'll be the first component. And then the other one's sort of permuted in the usual fashion. Okay, maybe I won't write it down. All right, so this is a function of variable t. This is a vector valued function of a variable t. And what we're interested in is, what would be very useful for us is, how are we going to differentiate these 2 things? Let me call this one, say, u of t, which is really also a vector. All right, so we have some useful lemma. All right, so in this context here, if I want to take f prime of t, okay, so that's r dot s prime, really. Then the formula is that it's r prime of t dot s of t plus r of t dot s prime of t, where the primes are always derivatives with respect to t. That's the first one. And the related formula for the cross product is if we take this vector valued function u and we differentiate it. Now that means differentiating in every component. Okay. Then what we're going to get is, so this is like r cross s prime, that's what we're doing. Then we're going to get r prime of t cross s of t plus r of t cross s prime of t. So it's just like the ordinary product rule that we know for functions of one variable, but extended to this sort of vector case. And the proof is just a simple computation where you just expand in coordinates and use the usual product rule. So as a consequence of this, a corollary that's going to be very useful for us is that if we have the situation where the quadrants of a vector field is constant, okay, by which I mean i.e. that rt dot rt equals c, which is constant for all t, or equivalently, if you want to take the square root, you can say it's the same thing as saying that the length of r of t is constant. Then r prime of t is perpendicular to r of t for all t. And the proof is an immediate consequence of this first formula. We just take the equation r of t dot r of t equals c and apply this formula. So we apply the lemma and we get that r prime of t dot r of t plus r of t dot r prime of t equals the derivative of c, which is 0 because it's a constant. And so since these two things are actually the same because it's a symmetric bilinear form, therefore r prime of t dot r of t equals 0, and that tells us that r prime of t is perpendicular to r of t. Okay, so it's a simple but useful little formula. All right, so we're going to be considering space curves. A space curve, perhaps alpha of t with coordinates x of t, y of t, and z of t. And we make a definition. We say that this curve is regular, alpha is regular, if alpha prime of t is not equal to 0 for all t. If the velocity doesn't actually ever become 0. The thing keeps moving. Okay. That's going to be a useful condition because we're going to be dividing by speeds occasionally. So another definition, that if alpha is a regular then we'll define t of t will be the derivative alpha prime of t all over alpha prime of t. So it's the derivative divided by the length of the derivative. So this is called the unit tangent vector. Okay, now we've said that we often want to reparameterize. So if we do reparameterize, using the arc length, so we have some curve that's doing something in space, alpha of t, and the t can be going faster and slower and doing whatever it wants to, but then we want to reparameterize it by just using the arc length. So that's 1, 2, 3, 4, just length starting from wherever we're starting. Then that new parameterization is called arc length. Okay, and so we're going to reparameterize using arc length, and we're going to usually call that S, to get a curve that will write beta of S. So it looks slightly different because we've renormalized it and using S instead of T. So this is now a unit speed curve. So then the length of its tangent vector is going to be 1. And then this unit tangent vector is just beta prime itself. We don't have to divide by the length because it's already of length 1. All right, so we've done that. We've renormalized. We now have this unit tangent vector. So it'll be a tangent vector of length 1. At every point, there's a little vector of length 1. And at some general point, S, that vector is going to be called T of S. Okay, so the next thing we want to do is we want to think about the derivative. So then from our corollary, beta double prime of S, which is the same as T prime of S, is perpendicular to T of S. All right, so our lemma says that if we have a vector function which always has the same length, in this case T of S always has length 1, then its derivative is going to be perpendicular to itself. Okay, so motivated by the case of the unit circle, where the length of this derivative was the curvature, we're going to define the curvature. Define the curvature K of S to be the length of this derivative of the tangent vector. So K of S is the length of T prime of S. So in the case of a circle of radius A, that was 1 over A. That was really the curvature. And this allows us to define this more generally. So let's have a look in this situation here. What are these derivatives going to look like? So over here, the curve is not bending very much. So the derivative of this T of S, the rate of change of the TS is going to be in this direction, but it's going to be relatively small. Okay, so here the vector, we're talking about now, we're now calling the curve beta of S, so let's just stick with arc length. So we have T of S are the blue ones, and then we have this the derivative T prime of S, okay, which is always going to be perpendicular to the tangent vector, but may have different lengths. So here, for example, the curve is curving more, so we're going to expect a bigger derivative, T prime of S. Over here somewhere, still have these unit tangent vectors. Here there might be quite a big T prime of S. Okay. It's just the acceleration of the curve, and the size of that acceleration is the curvature. Okay, that's good. And now we're in a position to renormalize to get a unit normal vector, because remember we want this sort of tripod of 3 unit vectors. We already have a unit tangent vector. We now want a unit normal vector. So far we have a normal vector, but it's of different lengths depending on the curvature. So we're just going to renormalize. So renormalize to define n of S to be this, well, beta double prime of S over its length, which is the same thing as T prime of S over its length, and its length is the curvature. Okay, do I have a little bit of red here? Yes, I have a little bit of red. Okay, so now I can renormalize. Yes?
Sorry, Alan. Would we need like an extra condition like that A dash has to be regular as well for us to be ensured that that unit normal can exist?
Yes, so we require that this curvature be non-zero, because we're dividing by this curvature. So if this curvature becomes 0 at some point, well, then it's problematic. Yeah, you're absolutely right. All right, so in this red here, I'm going to now show you the normalized vectors, and they're all going to be the same unit length. We're saying that's roughly 1. So here they are. They're all going to be perpendicular to the tangent vectors. So in these red, these are the new vectors that we're calling n of S. Yes?
Do most curves have a unit speed parameterization?
Yes, because given any curve whatsoever, we can just compute, we can write down an integral that allows us to calculate, at least numerically, the arc length. Yeah? And so basically, finding a unit speed parameterization is roughly equivalent to being able to integrate the length of the curve. Now, in practice, maybe I should say, most actual polynomial curves or curves that come up in space, it's very hard to explicitly give formulas for such a reparameterization exactly all the time. Okay, but in principle, we can.
If the parameterization is continuous, does that mean?
Yes, so all our parameterizations are continuous here. We're all talking about nice continuous curves. fact, nice and smooth curves. We don't want them to have too many jagged bumps, because then we're not being able to differentiate. All right, great. So we have these two vectors, and at any point, n of s, let's say any point on the curve, n of s points towards the center of curvature. So we could go a certain distance along there to find the center of curvature. That's the center of the osculating circle. It's the same concept as we had in the planar case, except it still is valid in the spherical case. So for example, over here, here the curvature is big, and so the radius of curvature is going to be small, so it's going to be a small circle there. Over here, the curvature was small, and so the oscillating circle is going to be bigger. Okay, but the normal is still pointing towards the center of the oscillating circle. And the oscillating circle can be found in the same way as we do for a planar curve. If we want to know what the oscillating circle at some point is, we choose any 3 points near there, say 1 point there and one on either side. Those 3 points, if they're not all collinear, will form a plane, and in that plane there will be a unique circle. And as the 3 points move together towards a specific point, that circle will take a limiting value, and that'll be the oscillating circle that we're talking about here. For this reason, the plane spanned by T of s and n of s is called the oscillating plane. The plane at any point spanned by the unit tangent vector and the unit normal vector is the oscillating plane. Of the curve at that point. So again, if we have some thing like this, then at any point, say that one there, there's a tangent vector, and I could also, by looking at the rate of change of this unit tangent vector, calculate the normal vector, and then the plane spanned by those two is going to be the plane, the oscillating plane. So as the point moves along the curve, there's this plane that moves with it that contains the direction of the tangent vector and also contains the direction of the normal vector. So this plane that's moving along, touching the curve, the oscillating plane. And that's the plane that contains within it the oscillating circle. All right, so we're doing well. We've got 2 out of 3, but we don't want to stop here. We want a third vector to complete our set. Maybe I'll leave this diagram here. All right, so we complete T of s, n of s by defining the binormal vector B of s, which is T of s cross n of s. This is another unit vector because t and n are perpendicular and they're both of length 1. They're perpendicular and both of length 1, so when you take their cross product, I remind you, you have to use right-hand rule to do that. Right? That means you have to use these 3 fingers, 1, 2, and 3. You put the thumb along the first one, which would be T, and then the second finger along the second one, which would be the N, and then the third finger, well, the third finger, there's T, there's N, and there's that B. Okay. So it's another unit vector, and they form a right-handed tripod, just like the I, J, and K of the usual basis vectors, but they can be sort of in any position. So there's a T in one position, an N in another position, T, N, and then the B would be coming out. Might do it like this, but that's supposed to be perpendicular to both of them. Okay, and they're all supposed to be of unit length. Okay, so therefore this set of vectors, the ordered set T of S, N of S, and B of S, is called the Frenet frame of the curve beta at S. All right, so we have to augment our picture by, we had, say, T's and N's, so T, N, so there's going to be a B coming out, also perpendicular. Here there's a T that way, an N in this direction, a B coming out, perpendicular to both. Here we have a T here, an N here. The beta is going to be going in the direction of the board. So at every point on the curve we have this tripod, these 3 vectors, and they're rotating around with the curve, and that's called the Frenet frame. And the Frenet equations are all about what happens to the derivatives of these 3 quantities, these 3 vectors. So the Frenet equations tell us what the derivatives are, and I might just write that down. So here are the Frenet equations. If you take T prime, N prime, and B prime, so we're going to do all 3 of them at once with a single equation, then that's going to be a certain matrix times T, N, B. And the matrix has mostly zeros, but there's a K here, and there's a minus K there, and there's a new thing called tau here, and minus tau here, and otherwise there's zeros. Okay, so that's the Frenet equations, where K is the curvature that we've already defined, so it's really a function of S. Everything here is a function of S. Okay, I don't always put of S, but everything is a function of S. And this tau is a new thing. Tau is the torsion of the curve. It's also a function of S. So I have to tell you what that is, and I have to tell you how you get these equations. Okay, one of these equations we already have. Okay, one of these equations is right here. Like the first one. The first equation says that T prime equals K times N. T prime equals K times N. That's exactly this equation right here. T prime equals K times N. And basically we defined N so that that was going to be the case. All right. So the first equation is T prime of S equals K of S times N of S. So I'll write down the S dependences so we make sure it's really everything is depending on S. Okay, and so that's really already known from the definition. Okay, so what next? Well, the next easiest one is actually the B prime, because it only involves a single entry. So let's have a look at B prime, and the claim is that this is a multiple of n. Okay, why is that? Well, we're going to have to do some differentiation. So it's not immediately obvious that this thing is a multiple of n. There's a sort of a bit of an argument that's involved. So the first part of the argument is that we first of all observe that b dot b equals 1. Okay, I'm not going to write the s everywhere. So b of s dot b of s is 1. This is a unit vector everywhere. So its dot product with itself is constant, and therefore we know from the lemma that we started out with that b prime is perpendicular to b. Right? Whenever a vector had constant length, then when we differentiate it, the derivative is going to be perpendicular to the vector from our lemma. Actually, I guess it was the corollary of our lemma. Okay, so b prime is perpendicular to b. But it turns out that b prime is also perpendicular to t. And how do we see that? Well, also, the second fact that we need is that b dot t equals 0. Right? B and t are perpendicular. So if we differentiate this equation, we get b prime dot t plus b dot t prime equals 0. But we know that t prime is a multiple of n. T prime is a multiple of n and b are perpendicular. Okay, so this is 0 since, well, t prime is k times n. So therefore, we conclude that b prime dot t equals 0. All right, so what do we know about this b prime? We know that it's perpendicular to b, and it's perpendicular to t. Okay, we have these three vectors, t, n, and b, and they're changing. Okay, and we know that the rate of change of this one, the green one, that's the binormal that we're interested in, we know that that rate of change, b prime, whatever it is perpendicular to both the tangent and the normal, both perpendicular to itself and to the tangent vector. But there's only one direction that's perpendicular to b and the tangent vector. That's the normal vector. So we conclude that b prime is a multiple of the normal vector. So b prime is a multiple of the normal vector. So what we do is we define b prime to equal Well, we're going to just make sure this equation is true. Minus tau, maybe I'll write S. So B prime of S equals minus tau of S times N of S. So we define tau of S to be that multiple. We know B prime is a multiple of N of S. Let's call the multiple tau. It's sort of the way we introduce the curvature, actually. Same kind of thing. We saw that this had to be a multiple of that, so we introduced that. So we're going to introduce now tau in the same kind of spirit. And we call this the torsion. And that takes care of our third equation. So now we have only this second equation to deal with. So finally we have to evaluate. We need to evaluate n prime. Okay, so remember we have this frame here. So we have T, and then we have N, and then we have B. This is a right-handed system. T, N, and then B. So we're interested in getting control of N prime. So we're going to write N as the cross product of, and we have to just make sure that we get them in the right order. So here's T, and here's N, and here's B. So if I do B times T, I'm going to get N. So N is equal to B times T, cross product of B with T. Yeah? It's like I times J equals K, J times K equals I, K times I equals J. It's sort of cyclic like this. Okay, so that's an expression for N. We can differentiate that using the fact that we know how to differentiate a cross product. So N prime is going to be the derivative of B times T plus B times the derivative of T. All right, well, we know what B prime is. We just already said that it's minus tau of S times N. So we still have to do minus tau of S times N times T. I don't really need the S because I'm dropping all the S's. So let me just write minus tau of N times T, plus B times the derivative of T prime, we can read from the first one, is K times N. Okay, now we still have to do these cross products. So again, the right-hand rule, T, N, and B. All right, now we're doing N times T. That's going to be, well, T times N is B, so N times T will be minus B. Okay, so this is going to be a tau times B because the minus sign from this one will cancel with the minus sign from that one. And B times N, T, N, and B. So B times N will be minus T, I think. Yes. So plus K times minus T for a total of minus KT plus tau B. And that is our second equation in the Frenet equations. That tells us that N prime is minus K times T plus 0 times N plus tau times B. All right, so those are the Frenet equations. And might take a little break, and then I'll come back and do an example just to have see how it goes.